So last class we looked at the electron configuration of different elements. Today we're going to look at how that electron configuration sets up the reactivity of those elements and really helps establish the periodic trends within the periodic table. So chapter 6 is due Sunday, so just one assignment is due this weekend. Just chapter 6 is due on Sunday, June 14th at midnight. I'll have office hours today, noon to 1:30, and then we plan to finish Chapter 7 on Monday. So next week you'll have Chapter 7 and Chapter 8 due. But for this week, just Chapter 6 due, which we finished earlier in the week. So the objective for today, we're going to determine the source of the periodic trend, and we're going to look at how the electron configuration helps establish the different reactivity patterns that we observe for different elements. So to understand where some of those trends come from and with respect to reactivity and the organization of the periodic table, let's take a look at one family. So if we look at helium, neon, argon, and krypton, they are all noble gases. And if we look at the electron configuration of those four elements, we'll notice that they all have a full outer shell. Well, what do we know about noble gases, right? We know that noble gases are non-reactive. Right? Why are they non-reactive? For a reaction to occur, we need to have some exchange of electrons. I need to lose electrons, gain electrons. Noble gases, they are non-reactive because they do not want to gain electrons. They have nowhere to put them. Their outer orbitals are full, and they also do not want to lose electrons, also because their outer orbitals are full. Let's take a look at another family, right? Group 1, everything in group 1, so lithium, sodium, potassium, rubidium, and even if we went down to cesium, we'll notice that in their outer orbital, they have one electron. We have one s electron in the outermost s orbital that we have occupied. What do we know about group 1? We know that all of these group 1 metals, when they react, they will form an ion with +1 charge. Right? So all of these group 1 metals, they're very reactive, and when they react, they're going to lose their outermost electron. So now we can start to get a better idea of where these trends come from. All of these elements in this family, right, lithium, sodium, potassium, rubidium, they all have one electron in the s orbital, and when they react, they lose that s electron, forming a +1 cation. Right, we can move one row over with the alkali earth metals. Right now, if we want to look at the alkali earth metals, we said when these react, right, here I just have beryllium, magnesium, calcium. I could certainly keep adding on to that if I wanted to. But group 2A, when they react, right, react to form a +2 cation. So our group 2 metals will lose 2 electrons. When they lose those 2 electrons, they're going to take a charge of +2. So everything in that family, when they react, they're going to lose their outermost electrons. They only have 2 of their outermost electrons. They're going to lose them both to form a cation that's got a +2 charge. So now, right, our reactivity is tied to how many electrons can we gain? How many electrons do we want to lose? Now we can start to see that all of these families, they're organized based on how many electrons we have, and that's what determines the reactivity type. Do I want to form a +1 cation, a +2 cation, or do I want to gain an electron, or do I neither want to gain nor lose electrons? So we can start to get a better idea of these periodic trends based on the electron configuration of each group. And the electrons we're looking at to help determine this reactivity, those are our valence electrons. Our valence electrons are the outermost electrons. Basically, the electrons beyond the noble gas core electrons. These are the electrons that are lost or gained during a reaction. Just our valence shell electrons. And just taking a look at that real quick, here's the electron configuration of sodium. Sodium is 1s2, 2s2, 2p6, 3s1. So our valence electrons for sodium are the outermost electrons, the electrons beyond the noble gas configuration. Here's my noble gas core electrons, right? That's my electron configuration for neon. I'm not going to touch those electrons, but I can work with the outermost electrons. I can lose those, I can gain those. Those are my valence electrons. So for sodium, I have one valence electron. It's the 3s1 electron for sodium. I can lose that electron, forming sodium plus 1. So here's a question for you. What are the valence electrons for vanadium? Vanadium is element number 23. So taking a look, element 23, right, we can figure out our valence electrons because our row, right, tells us what one we're working with. Well, vanadium is in the 4th row, so I'm looking for something that starts with 4. So I can cancel out B and D, and I can also break up the periodic table based on what orbitals I'm filling. So here I'm filling s orbitals. Here I'm filling my p orbitals. And here in the inner core, I'm just going to change the color and the transition. Right here, I'm filling d orbitals. So for vanadium, I've filled the 4s1, 4s2. That takes me to calcium. Now I'm filling 3d because remember, after 4s becomes 3d in energy. So 3d, 1, 2, and 3. So 3d3. Because vanadium has to have 5 valence electrons. I am 1, 2, 3, 4, 5 over. So I need 5 valence electrons. 4s2, 3d3 is the valence electron configuration for vanadium, right? That's what I have beyond my noble gas configuration. My noble gas configuration of argon, I'm not going to touch those electrons, those first 18 electrons. The outermost electrons are the last 5, the 2 in the s orbital and the 3 in the d orbital. So as we can see, elements in the same group generally have similar chemical properties, generally have similar reactivity based on their valence electron configuration. How many electrons do they want to lose or gain? That being said, however, their physical properties may not always be the same. And so just as an example, right, group 6, the chalcogens, oxygen, sulfur, selenium, tellurium. Oxygen at standard temperature and pressure is a gas, sulfur is a solid. So even though they have similar reactivity, their physical properties are often different. And so it was this reactivity that Mendeleev really used to help get together the periodic table of the elements, the early periodic table. For example, Mendeleev knew silicon. Silicon existed. They knew the properties of silicon. There was a void in his periodic table underneath silicon. Because of periodicity, because of this repeating reactivity pattern, he knew the properties of silicon. And this blank that was in the periodic table was underneath silicon, so he knew that this element underneath silicon had to behave in a similar way to silicon. And so based on that knowledge, he predicted that this unknown element, right, so in 1871, he made this prediction that this element is kind of like silicon. It's going to have an atomic weight of 72. It's going to have a density of 5.5. It's going to have a reactivity of oxygen where it will form this unknown element O2, and it'll have a reactivity where it'll form a tetrachloride. It'll react with 4 different chlorides. So 15 years later, that element was discovered. It was discovered and named to be germanium. It had an atomic weight of 72.5. It had a very similar density, very similar specific heat and melting point. And because of reactivity, right, it reacted with oxygen in the same way that he predicted, and it reacted with chlorine in the same way that he predicted. Because of this periodic table and the periodicity, both of those elements were going to have identical valence electron configurations, different energy levels, but the same number of valence electrons available. And that's what's dictating the reactivity of both of those. So that sets up 3 periodic trends: the trend in atomic radius, the trend in ionization energy, and the trend in electron affinity. Today, we're only going to look at one of those 3 trends. Today, we're going to talk about the trend in atomic radius in the periodic table, and then the next lecture on Monday, we're going to get into ionization energy and electron affinity. So atomic radius, if we look at the periodic table, there are 2 trends with atomic radius. So within each group, right, as we go down a group, atomic radius increases. That's our one trend within the periodic table. And the other trend is within each period, so within a horizontal column, right, our atomic radius increases from right to left. So atomic radius increases down a group, and atomic radius increases across a row from right to left. Those are the 2 trends for atomic radius. I increase as I go down a group, so that means that lithium is bigger than hydrogen, sodium is bigger than lithium, potassium is bigger than sodium, and so on. And the same thing as I'm working across the column from right to left. As I get closer to the left, I'm dealing with a larger atomic radii. And so here are the 2 trends we see, right? As we go down a group, my atomic radius increases, and as I go from right to left in the periodic table, my atomic radius increases. The 2 important trends: atomic radius increases, I'm just writing it again because it's that important, down a group, and right to left across the periodic table. So now we need to look at why does that happen? Why does the atomic radius increase as I go down a group? And why does the atomic radius increase as I go from right to left across a row in the periodic table? So the 2 factors that help determine the size of an atomic radius are the principal quantum number n, which is how big are our orbitals, and then the second component is effective nuclear charge, or Z effective. Basically, how much do those outer electrons experience the pull of the nucleus? So the first component, my principal quantum number n. As n increases, so does the size of the orbital. And that increases the atomic radius. Right, remember from the previous chapter, n is the size of our orbital. So if I have my nucleus, right, here is n equals 1, here is n equals 2 orbital, here is my n equals 3 s orbital, and here would be, right, my n equals 4 s orbital. As n increases, the size of the orbital increases, That's going to make a larger and larger electron cloud, right? Larger electron cloud. Larger atomic radius. The second component is my effective nuclear charge, Z effective, and that's basically how much do the outer electrons experience, right, the attractive pull of the nucleus. And for this one, let's think of magnets, right? My nucleus is positively charged. It's a big positive charge. My electron is negatively charged, and I'll just draw one, right, at a couple different energy levels. If I have those two magnets really close together, right, the attractive potential between those two magnets, if they're really close together, there's a strong attractive potential. So I'm pulling, that positively charged nucleus is able to pull the negative electron very close to it. As I move that electron farther away, here's the electron at a different energy level. As I move that electron farther and farther away, right, there's less attraction between the electron and the nucleus. The same thing for magnets. I move those two magnets farther and farther and farther apart. There's less attraction between the two magnets. There's less attraction between the positively charged nucleus and that negatively charged electron. That is your effective nuclear charge. So the closer the electrons are, the more they're experiencing that positively charged nucleus, and the tighter, right, the nucleus is able to hold on to them and pull them together. The farther the electrons are away, the less they're experiencing that positive charge from the nucleus. And so here is that information just displayed in a little bit different fashion about the change in atomic radius for atomic number. And as we can see, as I go down a group, right, so my first group, hydrogen, lithium, sodium, potassium, rubidium, right, I get an increase in atomic radius. So down a group, an increase in atomic radius because I'm getting an increase in quantum number. So here's n equals 1, here's n equals 2, n equals 3, right? And we get a jump and a jump and a jump each time. And we can see the other atomic trend as we go across the periodic table, right? From right to left, I see an increase in atomic radius. So as I go from right to left, an increase, a right to left, an increase, right to left, an increase. And that's the general trend. Yes, there are some outliers to that trend, but the general trend is an increase in the atomic radius. So that's what we've been talking about, right? I got an increase in atomic radius down a group. Because I have a larger quantum number, the larger quantum number results in a larger orbital. And that's what we see, right? Each break, larger orbital, larger orbital, larger orbital. And each time we see a big jump in atomic radius. And then the other trend is my effective nuclear charge. And I get an increase as I go from right to left in the periodic table. And so what is this effective nuclear charge? How should we think about this effective nuclear charge? And essentially what it is, it's basically how shielded is that outer electron from the nucleus. And the more electrons that outer electron has between itself and the nucleus, the more shielded that electron will be. And so looking at sodium, for example, the electron configuration of sodium, I have 10 core electrons, so those are my shield. And I have one outermost electron. So those 10 inner electrons, they're creating a shield buffering the outer electron from the nucleus. Those 10 electrons are shielding this outermost electron because between the nucleus, between the positively charged nucleus and that outermost electron, I have these 10 negative charges blocking some of that positive charge. And so we can actually calculate that. We can calculate the effective nuclear charge. And all that effective nuclear charge is basically Z minus S, where Z is the atomic number and S is the screening constant, where that screening constant is how many core electrons do we have? So for sodium, my effective nuclear charge, well, I have 10 inner electrons that provide my screening constant, and I'm atomic number 11, so I have 11 total electrons. So my effective nuclear charge is atomic number 11 minus 10 inner electrons. Basically, that outer electron is going to feel a charge of approximately +1. What does this mean, though? To get a better understanding, I'm going to write out the electron configuration of magnesium. Magnesium is the next element over. It is 1s2, 2s2, 2p6, 3s2. Now, magnesium has one more electron, but it still has the same number of core electrons. So my Z effective for magnesium would be, well, I'm atomic number 12 now. I've got 12 total electrons, but I still only have a shield of 10. So now my outermost electrons are going to experience a charge of not +1, but +2. So as we go from left to right across the periodic table, Z effective increases. My nuclear effective charge increases. Those outermost electrons are experiencing more positive charge from the nucleus. They're going to be held tighter. They're going to be held closer to the nucleus. That's going to decrease my atomic radius as I go from left to right across the periodic table. Because each electron I'm not adding to the core until I start a new row in the periodic table. To get a better idea, I'm going to just draw out one more picture as a way to think about what is this effective nuclear charge. We can think of this effective nuclear charge as a light bulb and a lampshade. And I'm going to just draw out, we're going to compare lithium to beryllium. Beryllium is 1s2, 2s2. So if I were to draw the electron configuration for lithium, right, lithium atomic number 3, I've got 3 protons. Here's n equals 1, here's n equals 2. So I've got 2 electrons out here, and I've got in my 1s orbital and my 2s orbital, I only have 1 electron. For beryllium, beryllium's atomic number 4. So now I have a charge of +4. I've got 4 protons in the nucleus. Here's my 1s orbital with its 2 electrons. And now here's my 2s orbital with its 2 electrons. So what happened from lithium to beryllium? What happened was I got 1 more proton in the nucleus. So basically, the light bulb got brighter. What didn't change was the lampshade. The lampshade stayed the same thickness. But because the light bulb got brighter, I'm going to see more light. That's the same thing for beryllium. The light bulb got brighter, so I'm going to see more light. Well, the nucleus increased in positive charge, so these outermost electrons are going to experience greater positive charge. I'm shielding with lithium, I'm shielding a +3 with 2 electrons. With beryllium, I'm shielding a +4 with only 2 electrons, right? So the nucleus became more positively charged, my shield stayed the same. So as a result, those outermost electrons are going to experience a greater nuclear charge. Because of that, right? The light bulb just got brighter from lithium to beryllium, but the lampshade stayed the same, so I'm going to see more light from that. Those outer electrons are going to experience more light. So here's a question for you. In germanium atom, which electron will experience the greatest effective nuclear charge? An electron in which orbital? The 2s orbital, the 2p orbital, 3s, 3p, or the 3d orbital. So germanium is atomic number 32, so we're all the way over here. And the electron that's going to experience the greatest nuclear charge is the electron that's closest to the nucleus. So in this case, Choice A, the electron in the 2s orbital would experience the greatest effective nuclear charge. If it was a choice, 1s, right, would be even greater nuclear charge because that would be even closer to the nucleus. And anytime you're looking at these questions in class, we should also be thinking about the other side of this. So I asked you which electron would experience the greatest nuclear charge, so that's the closest to the nucleus. On an exam, I could ask you what electron experiences the least effective nuclear charge. Right, so let's just use the same 5 choices. Which electron experiences, an electron in which orbital experiences the least effective nuclear charge? Now to answer this question, right, it's the exact opposite. The greatest effective nuclear charge is closest to the nucleus. The least effective nuclear charge is farthest away. So in this case for germanium, I've got electrons in the 4s, in the 3d, in the 4p. So the orbital that's farthest from the nucleus of those listed is the 3d orbital. So this would have the least nuclear charge. And it's not listed, but 4s, right? 4s is also a possibility. It's not there. And all the way over here, we'd also have 4p electrons as well. That's also not a choice, but that would be the farthest from the nucleus. And that would experience the least effective nuclear charge if it was a choice. But of the choices given, the greatest effective nuclear charge would come from the 2s. That's the closest. And the least would come from the 3d orbitals. So the important things from today, we need to understand and explain the atomic trends and atomic radii. We're going to get to ionic radii on Monday and really understand where those trends come from, right? Increasing atomic radius due to increasing size of my orbitals and the impact of nuclear effective charge. So as we're going across the periodic table, I'm adding more protons, so the light bulb is getting brighter, but the shield is staying the same. The core number of electrons stay the same. So as a result, I would see more light from that brighter light bulb. The outermost electrons experience a greater positive charge from the nucleus, and they're going to be pulled more closely to the nucleus as a result. So the next class on Monday, we're going to finish Chapter 7. We're going to talk about ionization energy and electron affinity, the last 2 trends within the periodic table that we're going to talk about.